In the humid salt-crusted air of the Arabian Sea, the crew of the USS Abraham Lincoln maintains a rhythm of calculated silence. It is 2026, high above an Iranian drone, a fragile silhouette of composite materials and hostile intent attempts a radar lock. To a civilian it is a provocation, to an engineer it is a data point. The engagement does not last long enough for a human heart to skip a beat. An F-35C, Lightning II, a ghost in the machine of the sky, ends the interaction with clinical indifference. The drone operator miles away in a concrete bunker watches their screen flicker to static before they even realize their asset was being hunted. There was no dogfight, there was no cinematic maneuvering. There was only the cold, inevitable application of physics. We call this dominance, but that word is too loud for the reality of what happened. This was the execution of a blueprint. It was the result of a fundamental shift in the geometry of war, a shift that did not begin with the AI swarms of the 21st century, but in the shifting sands of the Persian Gulf 35 years ago. In 1991, the world looked at Iraq's Qari air defense network and saw a fortress. Baghdad was a city wrapped in layers of high explosive steel, a probability field, where the mathematical chance of survival for a conventional aircraft approached zero. The experts predicted a Vietnam in the sand, a long bloody attrition where American pilots would be traded for Iraqi concrete. To break this wall, the United States Navy had to solve a physics problem. We were not stealthy. We were massive floating targets sitting hundreds of miles away in deep water. The math was simple and brutal. If you send a human pilot into that airspace, at 200 feet he dies. So we changed the equation. At 200 hours on January 17th, the USS Pittsburgh, submerged in the absolute silence of the deep, broke the code of the silent service. A 3,000-pound missile tore through the surface of the water, violently transitioning from hydrodynamics to aerodynamics. This was the Tomahawk land attack missile. It was not just a weapon, it was a declaration. It was the moment the Navy decided that hope is not a strategy but calculus is. The logic was cold. A pilot is a priceless asset, the product of 20 years of training, intuition, and biological evolution. A missile is a receipt from a defense contract. To save the human, we had to send the robot. But the robot of 1991 was primitive. It didn't have GPS, it didn't have a camera. It utilized a system called Terracom Terrain Contour Matching. It was quite literally a map-reading robot that navigated by touch. It scanned the rise and fall of the desert floor, comparing the physical world to a pre-loaded digital matrix. If the profile matched, the missile knew where it was. It was brilliant, but it was blind. If the target moved, the missile hit empty sand. Compare that to the Predator we have today. The Tomahawk Block 5 Alpha doesn't just read a map, it hunts. It possesses a multi-mode seeker. A brain capable of circling a battle space for hours, waiting for the perfect moment to strike. It can track a destroyer maneuvering at 30 knots in heavy seas. We have evolved the sledgehammer into a scalpel. However, the missile is only the final note in a symphony of violence. Before the kinetic strike, the enemy must be blinded. In the corridors of the Pentagon, they call this the suppression phase. In the cockpit, they call it Magnum. In 1991, this was a psychological game. The EA-6B Prowler would flood the airwaves with electromagnetic noise, turning Iraqi radar screens into a blizzard of static. But jamming is only a delay. To truly dismantle a defense, you need the hard kill. The F-18 Hornets would launch harm missiles weapons that ride the enemy's own radar beam back to its source. Imagine the Iraqi operator. He knows that if he keeps his radar on to find the American planes, he is lighting a signal fire for his own death. The Magnum call forced a choice: stay on and die, or shut down and be blind. Most chose blindness, and once the enemy is blind, the door is open. Yet opening the door is not enough. You have to be able to reach through it. Consider the F-14 Tomcat, the legendary Top Gun fighter. In 1991, it was the deadliest air superiority platform on the planet. And yet during the biggest air battle of the century, the Navy forced it to sit on the bench. Why would you leash your most dangerous predator? The answer lies in the nightmare of blue on blue. The skies over Iraq were crowded, chaotic, and filled with the fog of war. The Tomcat's Phoenix missile was a long-range killer designed for the open ocean, for a war of clear lines. In the phone booth of Baghdad, firing a missile from 100 miles away carried the risk of hitting a wingman. The technology of 1991 couldn't keep up with the lethality of the weapon. The Tomcat was retasked to reconnaissance, becoming a high-speed set of eyes because it was the only thing fast enough to survive. It was a king in a war that didn't need a king. It needed a manager. Today, that gap has been closed not by muscle but by the network. We have moved from the speed of voice to the speed of data. In 1991, a pilot had to hear a voice on the radio, process the information, and look at his own screen. Today we have what engineers call NIFC-CA. It is for all intents and purposes digital telepathy. An F-35 can fly deep into enemy territory with its radar off invisible. It sees a target using passive sensors and beams that data back to a destroyer hundreds of miles away. The destroyer launches the missile. The pilot never pulls the trigger. The ship never sees the target. The pilot is no longer just a warrior, he is a router in a lethal network. This is the long reach, this is the shield. We have spent 35 years learning that distance is life. We learned that precision beats mass every single time. It is better to put one 500-pound bomb through a specific ventilation window than to carpet bomb a city block. But as we look at the machinery, the Tomahawks, the F-35s, the SM-6 missiles, we must not lose sight of why the machinery exists. American engineering is built on a specific philosophy. Machines are expendable. Humans are exceptional. We didn't build robots because we were afraid to fight. We built them because we value the life of the person in the cockpit. We cleared the path with silicon so that flesh and blood could survive to finish the job. The history of the Navy since 1991 is the history of removing the friction of war. We have turned the chaos of the dogfight into the cold certainty of geometry. But the question remains when the robots are exhausted and the data links are severed, who is left to hold the line? To truly appreciate the transformation of naval warfare, one must look past the sleek lines of the aircraft and into the inventory of violence. This is not a random collection of hardware. It is a layered ecosystem designed to dismantle a peer-of-the-peer adversary. In 1991, this ecosystem was in its infancy, a collection of specialized tools that barely spoke the same language. Today, it is a singular sentient organism. Let us return to the kill box. In the early hours of Desert Storm, the Iraqi air defense was not just a series of missile sites. It was a living, breathing entity. The centerpiece was the ZSU-23-4 Shilka. To the uninitiated, it is a tank with 4 guns. To a pilot, it is a meat grinder. It pumps out 66 rounds of high explosive steel every second. At that density, the sky ceases to be air and becomes a solid wall of metal. The Navy's solution was the standoff. This is an engineering term that defines the distance between a weapon's launch point and the target's reach. In 1991, the safety line was 50 miles. If you stayed 50 miles away, the SA-2 and SA-3 missiles couldn't touch you. But there was a catch: at 50 miles, you couldn't see your target. You were throwing stones in the dark. This forced the creation of man-in-the-loop weapons like the AGM-84 Islam. During the attack on the Qadiyah hydroelectric plant, the mission was a surgical nightmare: cut the power to Baghdad without destroying the dam and drowning thousands of civilians. The Navy didn't have a weapon for this, so they built a Frankenstein. They took the body of a harpoon missile, the eyes of a Maverick, and the data link of a walleye bomb. The pilot of an A6 intruder would launch the missile and then via a grainy monochrome screen and a joystick manually fly the weapon into a specific ventilation window. It was legendary precision, but it was incredibly dangerous. To guide the missile, the pilot had to stay close to the target, tethered to the weapon by a fragile radio link. He was a sniper who had to stand in the middle of a street to see his target. Today we have deleted the joystick. The modern successor, the LRASM long-range anti-ship missile, does not need a pilot to hold its hand. It is autonomous. It doesn't even need GPS, which can be jammed. Instead, it listens to the electromagnetic signatures of an enemy fleet, identifying the specific ship it needs to kill by the flavor of its radar. It maneuvers, it thinks, and it executes. But the most radical shift in the inventory isn't a new missile. It's the repurposing of an old one. Consider the SM-6. For decades, the SM-6 was a shield weapon fired from the vertical launch tubes of destroyers to intercept incoming threats. It was a defensive tool. In 2026, the Navy took this massive missile and strapped it to the wing of a Super Hornet, designating it the AIM-174B. This wasn't just a hardware upgrade, it was an exploit of atmospheric physics. When a ship fires a missile, the weapon wastes a massive amount of fuel just fighting gravity and the thick, heavy air at sea level. By launching that same missile from a jet at 30,000 feet, and Mach 0.9, we have removed the energy tax. The missile starts its journey already high and already fast. Every drop of its propellant is now dedicated to pure unadulterated velocity. We have turned the defensive shield into a hypersonic spear with a range of over 250 miles. The standoff line hasn't just moved, it has vanished. Yet, as the weapons become more capable, the burden on the human operator changes. In 1991, a pilot's primary skill was stick and rudder, the physical act of flying and aiming. In 2026, the primary skill is data management. The F-35 pilot in our opening scenario isn't fighting the drone. He is managing a flow of information. He is looking at a fused picture of the battlefield where every sensor from a submarine under the ice to a satellite in low Earth orbit is contributing to a single godlike view of the world. This brings us to the friction of communication. In 1991, information moved at the speed of a human voice over a radio. Bandits bearing 09020 miles. In that 3-second sentence, an enemy jet could have moved half a mile. The information was always decaying. Today, the data moves at the speed of light. There is no decay. There is only the truth. But what happens when the network goes dark? What happens when the telepathy of modern war is severed by electronic warfare or cyber attacks? This is where the ghost of 1991 returns to haunt the modern engineer. We have built a system that is terrifyingly efficient, but it is a system that relies on the long reach. If the enemy finds a way to cut that reach, we are forced back into the phone booth, the close quarters visual range chaos that the F-14 pilots feared over Baghdad. We are currently in an era where the machine can see further than the human eye can comprehend, but the human remains the only component capable of making a moral judgment in the face of ambiguity. We use the silicon to clear the probability field, but the final decision to pull the trigger remains a heavy biological burden. The question for the next decade isn't whether we can build a better missile. We already have. The question is whether we can build a human commander who can keep up with the speed of the data they are being fed. The shift from 1991 to 2026 is not merely a story of better sensors or faster engines. It is a story of geometry. In the Persian Gulf, the battlefield was a fixed map. Today, the battlefield is a fluid electromagnetic web where the very concept of a front line has dissolved. To understand the final stage of this evolution, we must look at the kill chain. In the era of Desert Storm, the chain was literal and mechanical. You found a target, you communicated its location, you assigned an aircraft, and that aircraft delivered ordnance. If any link broke, a radio malfunction, a cloud layer obscuring a laser, a pilot losing visual contact, the chain shattered. Today the chain has been replaced by a kill web. In a web there is no single point of failure. If an F-35's data link is jammed, a nearby UAV picks up the signature. If a satellite is blinded, a high-altitude balloon provides the coordinates. The information doesn't flow in a line. It saturates the environment. This is why the Iranian drone in 2026 never stood a chance. It wasn't just fighting an F-35, it was fighting an entire architecture of visibility. But there is a final sobering lesson from the history of the Navy's long reach. In 1991, at the conclusion of the air war, the massive 16-inch guns of the battleships USS Missouri and USS Wisconsin roared for the last time in history. It was a spectacular display of dumb power, thousands of tons of steel lobbed at the horizon. It was the end of an era where mass was the primary metric of strength. We learned that 1,000 shells are less effective than one missile that knows exactly where it is going. We learned that the most expensive part of a weapon system isn't the explosive, it's the certainty. However, as we move into the age of autonomous swarms and AI-driven targeting, we face the efficiency paradox. The more we automate the war, the more we distance ourselves from its consequences. In 1991, the pilot guiding the SLAM missile via joystick saw the smoke, saw the target, and felt the weight of the moment. In 2026, the engagement is often just a notification on a glass cockpit display. The Navy decoded philosophy is simple. We study the machinery to understand the people behind it. We build the shield and the long reach, not because we seek conflict, but because we seek to make conflict so mathematically lopsided that the enemy chooses not to engage. We clear the path with silicon. We dominate the geometry. We turn the chaos of the desert and the sea into a blueprint for survival. But at the end of every data link, at the heart of every carrier strike group, there is still a human being making the most difficult choice in existence. The machine provides the reach, the human provides the reason.